Okay, let's go ahead and get started. So what I want to do today is just spend a little bit more time discussing what we began to think about at the end of class last time, which is a perturbative strategy for computing the observables in a quantum field theory, namely the expectation values in the vacuum of a product of field operators in an interacting quantum field theory, order by order in the coupling constants of the theory. Okay. So just to remind you of what we're interested in computing, so we wish to compute the observables, say the time-ordered vacuum expectation values of some product of field operators, so which I will, for the sake of brevity, just denote phi 1 up to phi n for this class, just to make some of the formulas a little bit simpler. These are the natural observables in a quantum field theory. As we discussed earlier when we talked about the LSZ formula, if we essentially take a Fourier transform of these guys and multiply them and apply some number of Klein-Gordon operators, that will give us some initial to final scattering amplitude. Or if we just wish to work directly in position space, we can just imagine these as the natural observables of quantum field theory. And what we began to develop last time was a systematic strategy for computing these using what are known as the position space Feynman rules. Okay. And these Feynman rules were derived using a set of relationships between different correlation functions known as the Schwinger-Dyson equations, which were derived only assuming the canonical commutation relations of a quantum field theory, namely that the equal time commutator of phi and the time derivative of phi is equal to delta function. Okay, that's the quantum field theory analog of the canonical commutation in quantum mechanics between x and p. And just to remind you of what these Schwinger-Dyson equations looked like, they said that if you take this Klein-Gordon operator and act it on some correlation function, some vacuum expectation value, where this Klein-Gordon operator acts only on the first field, and then you have a bunch of other fields going along for the ride, then what you get is one term coming from the interactions. So you get an interaction term, which is what you would expect from the classical equation of motion, which says that the Klein-Gordon operator acting on a field is not zero in an interacting quantum field theory, but instead is some function of phi. So for example, in a theory with a phi cubed interaction, this was equal to phi squared. And then, in addition to this classical term, we had some quantum mechanical correction terms. So minus I h bar, if we feel like using units where h bar is not equal to 1, times a sum of terms so with a delta function, this coming from the commutator, and essentially what one does is removes, using the commutation relation, a phi x and one of the phi i's from this commutator. Okay. So, for example, if you wanted to take this to study a two-point function, then if you acted this on a two-point function, you would get, here you would just get a delta function in this term, because you would remove two of the fields when you contract them, and here you would get some interaction term that would depend on the specific interacting theory that you're studying. So, for example, in a phi cubed theory with a quadratic interaction term, this would give you, this L prime would give you something that's quadratic in the fields. Okay. And so we use this to derive an algorithm, or at least to guess an algorithm for the computation of phi 1 up to phi n. And the algorithm was the following. So I'm just going to write down the algorithm that we guessed at the end of class last time. We guessed this algorithm based on one computation of a two-point function. What I'd like to do is just sort of convince you of the correctness of this algorithm, is just to give you another example today of this algorithm applied to some three-point functions. And then I'll talk in a little bit more detail about some features of the Feynman expansion in perturbation theory. And in particular, what I'd like to do is talk about how we use it in momentum space rather than position space. And actually, in momentum space, Feynman diagrams are that's really going to be the bread and butter of this course. Okay? And that's what we'll be starting to introduce by the end of class today. Okay? But the basic algorithm that we use when constructing Feynman diagrams is the following. Okay? So you start with external points for each position, say x1 up to xn, appearing in this correlation function. So, for example, if you're computing a two-point function, you would draw some set of external points with lines coming off of them, like this. And then you construct a diagram using the rules that lines can connect to other lines or split at an interaction vertex and in a phi cubed theory they can split into two. Okay. So, for example, you could have a split that looks like this, where you introduce another vertex here, and then each of these interaction vertices introduces a factor of I times the coupling constant G. Okay. Where here we're working in a phi cubed theory, so the interaction vertex was G over 3 factorial times phi cubed, so this L prime was G over 2 times phi squared. So here, that's with the interaction G over 3 factorial times phi cubed. And then associated to each line, we have a propagator. And I should emphasize here we have a free propagator that we call d xy, which is the propagator between two positions x and y. And the final rule is that the internal positions, or the internal interaction vertices, will be integrated over. Okay. And then the final expression for the correlation function is the sum over all diagrams constructed in this way with only one subtlety, that each diagram is multiplied by a numerical constant called its symmetry factor. And this numerical constant is just there to keep track of the various numerical constants that appear when you compute these propagators using, for example, as we did yesterday, the Schwinger-Dyson's equation, or as we'll do starting next week, Feynman path integrals. Okay? So right now, what I want to do is just define for you the symmetry factor and give you a few examples of these computations of Feynman diagrams before we then go back and talk about some more of these details. Okay. So the symmetry factor of a Feynman diagram is the number of ways that one can permute the various propagators in a Feynman diagram holding the external vertices fixed. For example, last time what we did is we computed the two-point function of two scalar fields, and we found that there was a leading term, which was just the free propagator. So I'll just label these by 1 and 2 rather than x1 and x2. So what is this? This is d12. And then we found various terms that were quadratic in the coupling. So there were 3 of them that looked like this. So here that's 1, 2, with some independent points that are some internal points that are integrated over. Oops. And then there are various symmetry factors associated with these diagrams, which are the number of ways that you can permute the diagram holding the external vertices fixed. Okay. So for example, this diagram has a symmetry factor of 2 because you can flip, here, let's see if I can draw that. You can flip these vertices. You can flip those two propagators. Meaning that there's one, so that there's sort of 2 permutations, namely the trivial permutation where you don't do anything, and the non-trivial permutation where you flip those diagrams so that there's 2 inequivalent diagrams where where you can permute this diagram holding the vertices fixed. So there's a symmetry factor of 2. And likewise, this guy also has a symmetry factor of 2. Whereas this diagram here has a symmetry factor of 4. Because you could either flip that guy or you could flip this guy. Okay. So if we use these rules, then we see that this is just equal to the free propagator minus g squared times the sum of 3 terms, each of which involves an integral d4x and an integral d4y. And then this first term is 1/2 d1x dxy squared times d2y, that 1/2 coming from the symmetry factor. That second term has a 1/4 because the symmetry factor was 4, because there's 4 independent permutations of that diagram holding the external vertices fixed. And then you get a d1x, a dxx, and a dyy, d2y. And that third diagram is a 1/2 coming from that symmetry factor times a d1y, a dy2, dxy, dxx. Okay. So we have a total sum of 3 different terms, each of which has 4 propagators and 2 internal points that are integrated over. Yes, is there a question?
Is symmetry factor, are you swapping x and y?
No, I'm sorry. What I'm doing is I'm permuting the lines, not the vertices. Okay. Yeah. Yes, thank you. Yes.
Can you just show me the 4 permutations you're talking about?
Oh, I'm sorry. Okay. What I'm doing, yeah, I mean, I guess the way that you want to think about it is that you're flipping, yeah, I guess the way that you would think about it is that you're flipping like that. It's sort of hard for me to draw. What you're doing is, let's put it this way. It's easier if you associate an arrow. So this is something that we're going to do in a few minutes when we talk about, here, let me do this a little bit more in a little bit more detail. So if you think about an arrow associated with each one of these propagators, then you can flip the direction of that arrow. Okay? So when we talk about Feynman diagrams in momentum space, we'll use these arrows to denote the momentum of a particle. So we'll think about this little loop as a particle, and that'll be the momentum of the particle, and then you can just flip that arrow. Okay, you can flip the direction. So okay, good. Okay, and so for example, if I write down this diagram here, this really has a symmetry factor of 4 because I can either have the arrow going down here and down there, or I could have one down, the other up, or the first up, the second down, or them both up. So there's 4 inequivalent diagrams. Okay. I mean, this is really just some stupid combinatorics. Okay. The reason why these symmetry factors are present, well, the reason why these symmetry factors are present is that we've introduced in, so we always normalize our interaction terms so that they look like, so for example, g over 3 factorial times phi cubed, or lambda over 4 factorial times phi to the 4th. Or if you have multiple fields, let's say you have a phi to the 17th and a chi to the 42nd interaction term, so 17 phis can scatter into 42 chi's, then you might have some coupling and you would divide by 17 factorial times 42 factorial. And when you work out all the different ways that you can construct diagrams coming from this, that factorial is there precisely because when you work out the number of different diagrams you can come from that will arise, you'll have a 17 factorial and a 42 factorial. But if your diagram has symmetries, okay, then it will actually arise fewer times than a generic diagram. And so these symmetry factors are necessary just in order to account for this fact. Okay. So, so far I'm just introducing this as an arbitrary rule that we're going to follow. And in another few minutes, I'll give you another example where I explicitly work out using the Schwinger-Dyson equations a couple, a different interaction. Okay, in this phi cubed theory. And again, you'll see explicitly these symmetry factors popping out. But a little bit later, next week, when I give an alternate derivation of Feynman diagrams using path integrals, I think it'll be a little clearer exactly how it is that these symmetry factors arise. Okay. But at this point, you can just view it as some stupid little combinatorial rule that we're just observing, okay, and that we'll justify in a little bit more detail next week. Was there a question, or did I more or less? Yeah. That's yeah. Okay. Yeah, you could say it that way. That's right. Yeah. Good. Good. Other questions? Yes. Yes, that's right. That's right. Yeah. Yeah. Okay. That's right. So yes. So yeah. So for example, there are also other theories where they really do come, where the arrows really are directional, in which case it would not have a permutation symmetry. So for example, as we develop more complicated theories, there will be other bits of data that we have to include on these Feynman diagrams, and they'll get marked up in some ways, in which cases you have to take into account these markings when you calculate a symmetry factor. So as a very simple example, later on in this class I'll give you some examples of Feynman diagrams where you have two independent species of field. Okay. And in that case, you don't want to include permutations where one species of field is turned into another species of field. There's a question? Yeah.
Why do you point diagram is a factor of 2? You can draw there as both things. These are possible. So the second.
Well, because, yeah. This will be a little clearer when we introduce the momentum space Feynman rules. But because of conservation of momentum, okay, sort of has to circle around this way. Okay. And actually, yeah, that's probably not the best way to describe it. Yeah. This will be a little clearer next. This will be a little clearer when we write this out in momentum space. Yeah. Sorry, there's a question in back. Absolutely. Okay. So, for example, as we discussed, when we consider more complicated fields, we'll need to start marking these up in some ways, and the symmetry factors will account for that. Yeah. Yeah. Okay. Let's talk about. We'll get to those. So let's burn that bridge when we come to it. But so, for example, this gives a straightforward algorithm for writing down subsequent contributions to this at higher and higher order in perturbation theory. So I guess it's now just a fact that I'm going to assert that this algorithm works to all orders in the coupling constant G. Okay. So, for example, if we want to go ahead and study this two-point function in a little bit more detail, then you'll have a term that's of order G to the 0 that looks like this. And then you can prove that there can't ever possibly be a term that's linear in the coupling constant. Okay. So there'll be no terms of order G. And why is that? Well, that's because if you imagine that you introduce one coupling over here, one interaction vertex over here, then you'll get two different lines here, and there's only one line over here to contract them with. So you can't actually construct a diagram with two external points using only cubic interaction vertices. Okay. And then there'll be some terms of order G squared that I wrote down here. And then, if you think about it, there'll be no terms of order G cubed. Why is that? Well, it's, I think it's something that is not too hard to prove, that if you try and construct a diagram with two external vertices and only cubic interactions, then you need to have an even number of interactions in order for all of the legs to match up. Okay. So let's try and do that. So let's try and imagine that we only allow ourselves 3 interaction vertices. Okay, so there's one. I don't know. You could put another one right there, and then you could try and connect it with some vertex over there, and you have 2 vertices on one side and 3 vertices on the other side, and so there's no way that you can hook them all up without adding another external vertex. Okay. And so you won't be so surprised if I tell you that in general you can just prove using this sort of diagrammatic method that the two-point function in phi cubed theory is going to be an even function of the coupling. Only involves even powers of the coupling. And so, for example, at order g to the fourth, you'll have various terms, say like that. So here, I'm just sort of, you can, once you get used to it, you can just sort of start writing down these terms without even thinking about it much, and so on and so forth. Okay. So there are actually more terms at order g to the fourth, but those are just 3 of them that I've written down. Okay. So these are known as position space Feynman diagrams, and we can think of the internal lines as corresponding to particles, but they're not particles we observe because they're not particles that are connected to an external vertex. They're not particles that are connected to one of the points where we evaluate the correlation functions. And so we usually refer to these as virtual particles. So, for example, when we think about this 2-point function, the story that we tell ourselves is that you started by creating a particle at position x1. That particle moved to another position x. It split into 2 particles that traveled along 2 different trajectories and then recombined at point y before finally ending up at position 2. Okay, so that's the story that you tell yourself when you draw a Feynman diagram. Okay. And the reason why we sum over all possible Feynman diagrams is because in quantum mechanics, everything that is not forbidden is compulsory. Okay. A particle, a system will travel on all possible paths through configuration space between its initial and final endpoints. So there are a few more rules that I want to mention I've implicitly been assuming when I write down these position space Feynman diagrams. So I don't know what number did I get up to here. I got up to 4. This was maybe number 5. Okay, that'll be a 5. Okay. Rule 6 is that we always demand that our diagrams are connected to one of the endpoints. Okay. So, for example, we forbid things that look like that. Okay. So, if you think about it, all that we're doing when we forbid things that look like that is we're demanding that our vacuum state stays normalized. Okay. This will become a little more clear when we work out the Feynman rules using the path integral derivation, because in the path integral derivation, we'll need to keep track of the normalization factors that essentially tell us the norm of the ground state. And we'll see explicitly that you'll get bubble diagrams that will appear in your Feynman diagrams, but they will all magically cancel out, okay, once you normalize everything appropriately. But right now, it's just one more rule for you to keep track of in our perturbative expansion. Okay, so let me give you a second example of some Feynman diagrams using computed. First, I'll compute a correlation function directly using the Schwinger-Dyson equations, and then I'll give you its translation in Feynman diagrams, and we'll see that indeed it does agree with the rules that I've written down above. Okay. So let's consider, say, a 3-point function in phi cubed theory. Okay. Now, when I say phi cubed theory, what I mean is the theory where I have the interaction term g over 3 factorial times phi cubed. Okay. So first, let's go ahead and compute this guy directly using the Schwinger-Dyson equations. Okay. So again, I'm going to use this trick that I used last time. So I'll rewrite this in the stupidest way possible. Okay. So here I'm using the short notation where delta sub x1 is the delta function x between x and x1. Okay. And so all I've done is say that this function phi of x1 is equal to the integral d4x of delta x1 times that function of x. Okay. Now I can use the fact that our free Feynman propagator is just the Green's function for the Klein-Gordon operator. Okay. To write this as I times the integral d4x times dx squared plus m squared dx1 times this 3-point function. Then I can integrate by parts to write this as the integral of a propagator times dx squared plus m squared acting on this guy. And then I can use the Schwinger-Dyson equation, okay, which says that this is the sum of two terms, okay, the first of which comes by substituting in the interaction term. So that was phi x squared times phi 2, phi 3. And the second of which is the sum of two terms, both of which are delta functions, one of which is the delta function where x and 2 coincide, so that's a delta x2 times the expectation value of phi 3, with this, and then there's a similar term where x and x3 coincide, times the expectation value of phi 2. Okay. Now, I'm only going to be interested in evaluating this guy at linear order in this perturbative expansion. So I can use the fact that this guy is equal to its value in free field theory plus terms that vanish when the coupling is taken to 0. And in free field theory, an endpoint function is just given by the sum over all possible pairings between the points of the free propagators. Okay. This is what we introduced last time. This was called Wick's theorem. So this was, for example, equal to the propagator between two x's and the propagator between points 2 and 3 plus twice dx2 dx3. Okay. Or, in the language of Feynman diagrams, this is the statement that this is equal to, say, we have 2 points here, this guy plus this guy plus this guy, plus the final possibility where you have x connected with 2 above and x connected with 3 below. Okay. Okay. So that was this first term. And the second term, so let's compute, say, phi at x2. Or, so I guess it was 5x3 was the first one. Here, let me just write it like that. So to compute this guy, we can again, here, I'll just call this point z here, just to keep everything. So z could be either x2 or x3. So that's, I'll just write this as the integral d4x delta xz times the expectation value Is that a terrible notation? Am I going to run into trouble if I use that? No, I'm not going to run into trouble. I'll write it integral phi x. And then I could go ahead and use the exact same trick that I was using earlier. So this is then the integral d4x of dxz times the Klein-Gordon operator applied to phi x. So dx squared plus m squared on phi x. And that is given by the Schwinger-Dyson equation. It's just phi x squared times the coupling, so g over 2. Sorry, and there was an I here. So that's I, g over 2, times the integral d4x dxz times dxx plus various terms that are in the phi cubed theory of order coupling squared. These are the terms that we were computing above. Okay. So let's go ahead and plug this into our expression for phi 1, phi 2, and phi 3. So what do we get? Well, phi 1, phi 2, phi 3 is going to be a sum of a bunch of different terms. So you'll get a g over 2 out front, an integral d4x, and then you get these first terms. So you get a dx1 times, I hope I did everything correctly, a dx1 times a dxx d23 plus twice dx2 dx3. And then you have this term here. So I'll first use that delta function to do this x integral, but then I pick up another x integral down here. So I get a d12, that's this guy, because that x has now been set equals to 2, times this expression here, where z is equal to 3, so that's a dx3 dxx. And then you have this term here, which is the exact same thing with 2 and 3 switched. So that's a d13 dx2 dxx. Okay. Or let's just rewrite this a little bit more neatly. So that's an integral d4x times the sum of 4 terms. Okay. So you had a d1x dxx d23 plus a d2x dxx d13 plus a d3x dxx d12 plus twice dx1 dx2 dx3. So we want to write this all out in terms of our Feynman diagrams. Well, that first term has a propagator connected from 1 to x with an internal loop here connected to x integrated over, and then 2 and 3 are just connected by a normal propagator. And then we have 2 other terms, where now here in that second term 1 is connected to 3 and 2 was connected to some internal loop. And then we have a third term where 1 is connected to 2 and 3 is connected to some internal loop. And now we have a fourth term where all 3 of them are connected to a vertex. Okay. And then you have terms that are higher order in G. Okay. And you can check that all of the symmetry factors agree. Okay. So you have symmetry factors of a 2 associated with each one of these loops here. That gives you a 1/2 for this term, and this term. And then you have no symmetry factor for that diagram because there's no way you can permute the various propagators in that diagram holding the external legs fixed. So this was just another check that by using these Schwinger-Dyson equations, we can work out the perturbation theory for these various correlation functions, and we reproduce exactly what you would expect coming from these position space Feynman rules. So in your problem set that I'll be handing out next class, you'll have some more practice using these Feynman rules to compute diagrams. Okay? So let me make a couple comments based on this computation. Okay. So the first comment that I want to make is that because we derived this using the Schwinger-Dyson equations, it's clear how we can imagine dividing these terms up into terms that come from classical physics as opposed to terms that come from quantum physics. Okay. And the reason is that in the classical limit, the delta function in the Schwinger-Dyson equation disappears. And if you think about it, in the construction of these Feynman diagrams, it's this delta function that allows us to connect lines together to form loops. So, for example, this diagram, and this diagram were all constructed using delta functions that appeared from the Schwinger-Dyson equation, whereas this diagram was not. And so this gives you a rule that you should keep in mind when you think about the interpretation of Feynman diagrams. In particular, in a classical theory, what you have are only tree diagrams. So diagrams of this sort, which contain no loops. And indeed, if we had kept in our factors of h bar, we've set h bar equals to 1 here. If we'd kept in our factors of h bar, you would see that each of these three diagrams that contains a loop has a factor of h bar in it. Okay. And as you expand order by order in the Feynman diagram in the loop expansion, order by order in the coupling, each loop that you have comes with an additional factor of h bar. Okay. So when we do this perturbative expansion in terms of Feynman diagrams, not only are we doing a small coupling, small g expansion, we're also doing a quantum expansion, okay, where you start with a classical result and you add successively higher and higher powers of Planck's constant. That's not exactly obvious because we're using units where h bar is equal to 1. So I encourage you, for example, to go ahead and, in your free time, take the calculation I just gave you, restore all the factors of h bar, and check that all of the diagrams that came with loops were suppressed by a power of h bar. Maybe that'll be a problem on your problem set. This is the exciting thing about not having written the problem set yet. I can just keep claiming that I'm going to add stuff to it. Okay, good. Let's see. I think that might be all I wanted to say about position space Feynman diagrams. What I'd now like to do is move on to momentum space Feynman diagrams. Before I do so, let me pause and see if there are any questions. Yes?
So the only diagram that we have in this probability of phi 1, phi 2, phi 3 is this particular order before, right?
Yes, that is exactly right. Okay. If, for example, you were computing a 4-point function, then you would have a tree diagram like this. Okay. And I should emphasize, I mean, maybe this is something that I should say explicitly, which is that in, for example, theories with other interactions, other types of interaction vertex are allowed. So, for example, if you have both a phi cubed and a phi to the fourth interaction, then you would have both a cubic vertex as well as a quartic vertex. Okay. And so you can then check, for example, that if you wanted to compute this 2-point function, well, sorry, if you wanted to compute this 2-point function, you would get the free propagator, and then at linear order in the coupling, there's nothing involving order g, but there is something of order lambda, which looks like that. And then at quadratic order, well, there's all sorts of stuff. And so as you add more and more interactions, the types of diagrams that you get can become more and more complicated.
Circles that were disconnected, that would also
Yes.
count, right?
It would not. Sorry. The ones, okay. Yeah. So diagrams of this type, is that something that we're going to come back to in a little bit? Okay. So it's, right now we're including these in our Feynman diagram expansion because they are, so the rule is that you have no bubble diagrams, which are things that are completely disconnected, but you are allowed to have things, so all of the parts of your diagram have to be connected to at least one external vertex. Okay. But if you think about it, so if you remember when we discussed the spectral decomposition, one of the things that we demanded was that the expectation value of the 1-point function in an interacting field theory had to vanish. Okay. But what you see here is that in our interacting field theory, we're computing an expectation value of a 1-point function, and it's not vanishing. Okay. What does that mean? What that means is that in this interacting theory, you have to shift the value of the field. So remember, you can always shift the value of the field by subtracting off its expectation value in the vacuum, because it's the expectation value of the field in the vacuum is just a number. So when you start studying this interacting field theory, what you have to do is order by order, you're going to have to end up shifting the expectation value of the 1-point function to get this thing to vanish. Order by order in perturbation theory. Okay. This is renormalization. Okay. And so we'll be spending a lot of time talking about this later on in the semester. But right now what I'm just trying to do is give you the nuts and bolts way of computing these guys, order by order in perturbation theory. And I think it's fair to say that a lot of the rest of this semester in class is going to be working out the implications of this. Good. Yes?
So every correlation function has only one tree diagram, right? For example,
That is-
you have 3 fields, you have only one
That is
tree
correct. Yes, that's correct. I mean, well, okay. That is correct in the cubic theory. In a theory with 2 different interactions, say a cubic and a quartic theory, then these are both tree diagrams. Okay. So in theories with more interactions, of course, you could have many different classical tree diagram contributions to a given expectation value. Good. Good question. Okay. So not only does this work for theories with other sorts of interactions, this also works for theories with multiple fields. So far in this course, we've mostly focused on a single scalar field, but of course we live in a world where there are multiple different kinds of particle, multiple different kinds of field. So, for example, you could imagine a theory of two scalar fields. I'll call them phi and chi. Let's say they have masses m phi squared and m chi squared. And then you could imagine that they have some cubic self-interaction terms along with some interaction terms that allow phi particles to turn into chi particles. Okay. So there's a simple interaction term, something that's proportional to phi squared chi squared. Okay. And that will allow two phis to turn into two chis. Okay. So now if you write down the Feynman rules for this theory, we now have two types of external vertex and two types of possible propagator. A propagator for either a chi field or a phi field. And we have three different interaction vertices. Okay. So for example, you have this is your phi propagator. Oops. So let's say if you have points xy, this will be dxy, and I'll just maybe put a phi up here. So it's the propagator for a free field of mass m phi squared. And we could use a squiggly line to denote chi. So this would be the propagator between x and y of your field chi. So for example, the external vertices, so these would be our external propagators. The external vertices for phi would look like this. The external vertices for chi would look like this. And then the interaction vertices, well, you would have a 3-point phi vertex. Phi is represented by a straight line, so this would be equal to IF. A 3-point chi vertex. Chi I'll represent by a squiggly line. That'll be IH. And then you have a vertex that allows chis to turn into phis. So that'll give you an IG. Okay. And so then you can just go ahead and start computing things. Okay. So for example, the 2-point function for chi will include the sorts of terms that we're writing down above, plus other sorts of terms. So here, you'll have a term like that, okay, where you have an internal loop which is a phi rather than a chi, plus dot, dot, dot. Okay. So it's fairly straightforward to generalize these Feynman diagrams to take into account multiple fields. All you need to do is add additional labels to the propagators and vertices to account for the fact that you have multiple fields. So in this case, for each propagator that's a chi field, I've drawn as a squiggly line. Sometimes you'll see all kinds of different notations. Usually we use squiggly lines to denote photons or gauge fields, but really that's just a convention. Good. Any questions on this?
The second of those diagrams, that's a chi-forward.
Oh, I'm sorry, we don't have a chi-forward in the interaction. Okay, sorry. Yeah, sorry about that. Okay. In my notes, I had a chi to the 4th interaction. Okay, so this will be the thing that's linear. Okay, then you'll have various things that are quadratic. So these are the sorts of things that we were drawing before plus dot, dot, dot. That's the diagram that I meant to draw. Okay. So this guy is of order, what did I call that? Of order G. And this guy will be of order H squared. And then you'll have all sorts of other higher order couplings. Okay. So far we've introduced Feynman diagrams as a recipe for computing scattering amplitudes in position space, or sorry, correlation functions in position space. But what we'd really like to do is develop some sort of algorithm for computing scattering amplitudes. So remember, when we're studying scattering amplitudes, the name of the game is to compute the matrix element of what's called the S matrix, which is the amplitude for some initial state containing particles with some momenta to scatter into some final state containing particles with some other momenta. Okay. So in the LSZ formula, this was related to the sort of correlation functions that we've been computing so far by a Fourier transform. So here, what you do is, if you want to calculate, say, some scattering amplitude involving a bunch of initial particles with momenta pi and final particles with momenta x1 qi, all you do is you compute one of these time-ordered expectation values at positions x1, say up to xn, if you have n initial particles, and y1 up to ym, if you have m final particles, and you take the Fourier transform, inserting the appropriate powers, inserting the appropriate factors of this Klein-Gordon operator. So let's now try and take the algorithm that we wrote down in position space and understand how that would let us calculate these scattering amplitudes, which are really amplitudes in momentum space rather than in position space, because we label the initial and final particles by their momenta rather than by their positions. So to understand how this works, let's just consider some individual contribution from a Feynman diagram to just some simple two-point function. Okay. So let's just consider this guy here. So this is one of the three terms that I wrote down that contributed at order coupling squared to the two-point function between phi at x1 and phi at x2. Okay. And the question then is, how does this contribute to the scattering amplitude, where the initial state is just a state with one particle of momentum p, and the final state is a state with one particle of momentum q. Okay. So if we want to go ahead and compute this, let's just start by writing out this contribution here in momentum space. Okay. So we'll use the momentum space representation of the Feynman propagator. So we have a k squared minus m squared plus I epsilon times e to the I k x minus y. Just for the sake of making my formulas a little bit shorter, I'm just going to suppress the I epsilon factors for now. Okay. And then let's just go ahead and write out what this contribution to phi 1, phi 2 looks like using the expression for these four propagators in momentum space. So we had that minus g squared over 2 out front. We had an integral d4x, integral d4y. We have these various integrals. We have now 4 integrals d4k. So I'll call them k1, k2, k3, and k4 with various powers of 2 pi. Okay. And then we have the various propagators. Okay, so we have an e to the I k, x minus x1 over k1 squared minus m squared. That's this guy right here. And then we had an e to the I k, so that was a k1, e to the I k2, y minus x2 over k2 squared minus m squared. And then we have 2 other propagators. We have an e to the I k 3 x minus y over k3 squared minus m squared. And then we had an e to the I k4 x minus y over k4 squared minus m squared. Okay. Now, these propagators are invariant when you switch x and y. Okay, so I've chosen a particular ordering here, x1 minus x, and I could have said x minus x1 here. You know, to see that they're the same, I would just change variables, say k1 to minus k1, and you'd see that you'd get the same answer. I've chosen those particular signs for reasons that will become clear in 2 seconds. Okay? But that's just to make my life easier. The answer, of course, won't depend on that choice. Okay? So now what we'd like to do is use this to compute a contribution to the S matrix element, where you have one particle with momentum q in your final state, a particle with momentum p in your initial state. And what do you get? Okay, actually, even before I do that, let me just note that there are a couple of simplifications that I can do when I'm writing out this contribution to the 2-point function in momentum space. So in particular, I can actually just do the d4x and d4y integrals. Because the d4x integral is an integral d4x of an integrand, which is e to the I e to the I k3 plus k4 minus k1 times x. Okay. So the x integral just gives you a delta function that sets k1 equal to k3 plus k4. And likewise, the y integral gives you another delta function, because it's an integral d4y of e to the I y times k2 minus k3 plus k4. So that's delta 4 of k2 minus k3 minus k4. Okay. So you can see that if you actually multiply, so let's say that we used the x integral to do the k3 integral. So that would set k3 equals to k1 minus k4. You can then plug that into this expression here, and you would get a d4x of k1 minus k2. Okay. So I could write that contribution to the 2-point function as g squared over 2 times, I only have, so I'll write this as I'll do the d for x, d for y, and dk3 integrals, and write this as an integral d for k1, d for k2, d for k4 of a delta function that sets k1 equals to k2. And then most of those phase factors disappear. So all I'm left with is an e to the I k1 x1 and an e to the minus I k2 y x2. And then I have the various denominators. So times 1 over k1 squared minus m squared, 1 over k2 squared minus m squared. Sorry, I over k3 squared minus m squared. Remember, k3 squared is k1 minus k4 squared minus m squared, and I over k4 squared minus m squared. Everything clear so far? So we can now go ahead and plug this into our expression for the scattering amplitude. So if you want to understand the amplitude for a state with initial momentum q to scatter into a state with final momentum p, you need to do 2 more x integrals. Okay, we have an I integral d4x of e to the minus I. Okay, I might have mixed up what I called p and q here. Yeah. So above I was calling my final state something with momentum q and my initial state something with momentum p. So I have an e to the minus I p x1. And then we have the differential operator d by d x1 squared plus m squared acting on this correlation function. And then we have an I integral d x2 e to the I q x2 times d by d x2 squared plus m squared. All of this acting on phi 1, phi 2. Okay. And so the name of the game now is to go ahead and just plug this expression up here, which was a contribution to our 2-point function, into this expression for the LSZ formula, for the scattering amplitude using the LSZ formula. There's a couple of tricks that I can use. Okay. So the first thing is to notice that I could always integrate this term by parts to get it to act on this guy up here. And then you'll just get a factor of p squared minus m squared. And likewise, this term, integrating that guy by parts, will turn that Klein-Gordon operator into a q squared minus m squared. Okay. And then doing the x1 integral, okay, so here, let me just write this out a little bit more explicitly. Okay. So doing the x1 integral, so we have an e to the minus I p x1 here, and an e to the I k1 x1 up there, will give you a delta function that sets k1 equals to p. And then likewise, this x2 integral, you have an e to the I q x2 here, and e to the minus I k2 x2 down there, will give you a delta function that sets k2 equals to q. So when we do the x1 and x2 integrals, we get 2 delta functions that we can use to do the k1 and k2 integrals. And you'll get, well, a minus g over 2 out front. You have that delta function between k1 and k2, which is now between p and q, okay, because k1 was p and k2 was q. And you're left with an integral d4 k4 of a bunch of propagators. Okay. So the first thing that we should notice is that this term here was a p1 squared minus m squared. Okay. p1 is equal to k1, so that'll cancel this propagator here. Likewise, this q squared minus m squared will cancel this k2 squared minus m squared. And you're just left with these final two propagators. So you get an I over k4 squared minus m squared coming from this term right here, and an I over p minus k4 squared minus m squared from that second term. So the final result for the scattering amplitude is actually relatively simple. Okay. The first thing that I want to mention is that this delta function out front is exactly what we expect. This is the delta function that tells us that momentum is conserved. In particular, if you have a state with some initial momentum p, then no matter what you do with it, no matter what interactions it undergoes, it should still have a final momentum p at the end of the day. Okay? So it's impossible to have a scattering amplitude where some particle magically gains energy or momentum without some other particles coming in to give it to it, give that original particle energy and momentum. Okay? So to make the notation a little bit simpler, we'll typically write this S matrix just as 1 plus some powers of 2 pi to the 4th that unfortunately I was a little sloppy about writing up here, times a momentum conserving delta function. So you have to sum all of the initial momenta minus all of the final momenta, okay, times something that we call m, where m here is the scattering amplitude, which in this case has a contribution from the Feynman diagram I wrote above of minus g squared over 2 times integral d4k times I over k squared minus m squared times I over p minus k squared minus m squared. Okay. So at the end of the day, it's a reasonably simple expression. And we can associate this expression with a similar sort of diagram that we wrote down in position space. And it'll be a diagram that looks like this. Okay. So again, we have an initial particle. Okay. And a final particle. But now, instead of labeling the initial particle with a point that tells you where you insert an operator, you label it with a momentum. And I'll put an arrow there to denote that it's an incoming particle, and an arrow going out here to denote that you have a final particle with some momentum that I called q. But by the conservation of momentum, that q just has to be equal to p. And then you note that these guys in here, those are also just two different propagators, which I can associate with the two lines here and here. Okay. And the point is that by conservation of momentum, if this upper propagator has momentum k, and this guy has momentum p, if these interaction vertices preserve momentum, conserve momentum, then this guy down here has to have momentum k minus p. Okay. In particular, if you think about these internal loops as describing virtual particles, these virtual particles should still conserve momentum. Okay. So if you have a particle p that splits into two particles, then the sum of the momentum of those two particles better still be equal to p. And indeed, if you see what I've done here is I've demanded that, k1 minus p plus k has to be equal to p. Okay. So this is by conservation of momentum. Okay. So based on this, you can probably anticipate what the rules for computing scattering amplitudes using Feynman diagrams are going to look like in momentum space. Okay. So the Feynman rules in momentum space say that you start with one external line for each incoming or outgoing particle, labeled by its momentum, and then you allow lines to interact with interaction vertices which, for example, in the phi cubed theory, take the exact same form as we had in position space. So they're just factors of I times the coupling constant. And then the internal lines also get propagators. So just as in position space, each internal line got a propagator, here in momentum space, each internal line gets a propagator as well. The only difference being that we write the propagator in momentum space. So I over k squared minus m squared plus I epsilon, whereas external lines, unlike the case of position space, get no propagator. So the reason being that in the LSZ formula, you multiplied by a, so you had this differential operator here. Where was it? You had these differential operators here, and each one of these is precisely designed to cancel out a propagator. Okay? So that makes these Feynman diagrams in momentum space much simpler. Okay. So the internal lines get a propagator, the external lines get no propagator, and the important rule is that momentum is conserved at each vertex and undetermined momenta those that are not determined by momentum conservation are integrated over. And then, as in the case of the position space Feynman diagrams, you sum over all diagrams with an appropriate symmetry factor. Okay. So, for example, if you want to calculate the one-to-one scattering, where a particle of momentum p goes to a particle of momentum q, well, you get the trivial thing, okay, which is just gives you the 1 in the S matrix. And then you get a one-loop diagram, okay, where you have one undetermined momentum k that goes up top, and by momentum conservation, you have a momentum p minus k. on the bottom. Okay. And you can see I've written down the momenta there in such a way that their sum is equal to p, so that the ingoing momentum is still equal to p. And then you have an outgoing momentum, which again, by momentum conservation, has to be equal to p. Okay? Plus, so on and so forth. Okay. So one of the advantages of writing this in momentum space rather than position space is that the final answers that you get at the end of the day are really vastly simpler in momentum space. Okay. For example, when I wrote down this diagram in position space, it involved 2 x integrals and 4 propagators. When I write it down in momentum space, it involves 1 k integral and 2 propagators. And as you will discover when you start computing these things explicitly, that makes a world of difference as far as how difficult the actual computation is going to be. Okay. So I'm just about out of time. If this is all a little much, don't worry. You're going to get lots of practice with computing Feynman diagrams. It's really kind of going to be what we're doing for the rest of the year to some extent. So for that reason, I kind of want to, spend a lot of time, convincing you of the correctness and the utility of this approach to computing in quantum field theory. So starting next time, what I'm going to do is give you an alternate way of thinking about Feynman diagrams, the computation of these observables using the Feynman path integral approach. But maybe I'll just stop here and see if there are any questions. Is there a question? Yes.
The previous, on the second diagram, when you were phi minus k, on the pages before, you wrote the other way around.
Oh, did I? Wait, so what did I write the other way around? P minus k, k minus p? Yeah, sorry about that. Okay. No, you're right. The way that I've written it, that should be a k minus p. Right. So the rule is that I've drawn a little arrow to keep track of which direction the momentum is going. And you can see that the momentum k is going around like this. So that's a positive k. But this p here is going like this, and it's going the opposite direction here, which tells me that I have a minus p. Okay. So those arrows are there just to help us keep track of these signs. Good.
So the initial and final states, like if it's just one particle is scattering into another one,
Yes.
it's just 3 in momentum, right? But the initial and the final states as the Browski test.
Yes. Okay.
So then, you really don't have to keep track of it.
That's right. That's right. You really only have to keep track of 3 of the momenta, okay? Because if you have these, by Lorentz invariance, if you have 1 particle with momentum, 3 momentum p, then that automatically fixes its 4 momentum. Yeah. That's right. Okay, so we'll move on to path integrals next class. Okay. And I guess I was planning on giving a sort of brief review of path integrals in quantum mechanics. Would that be appreciated, or would it be resented? Appreciated? Okay, good. Okay, see you next class.